Oh, is it working? I did not think that would work the first time. Is it working? Anyone in the chat, can you tell me if it's buffering as much for you as it's buffering for me? Hey, Eric. Cool. It is buffering. Nice. Yeah. Anyone in the chat, can you tell me if it's buffering as much for you? this any better for anyone? Is this any better for anyone? Okay, cool. It just improved for me too. Okay. Wow, only 4 people here. Should we wait a bit, I guess? Okay, looks like I'm just gonna have to monitor on my phone. Oh, yeah, Eric, there probably was an echo because I was playing the audio on my phone while I was reading, so yeah. Okay, well, there are only 3 people here watching now, and I think one of them is me. And one of them is Eric. So, Neil, it looks like you're all alone. I feel like we should wait for more people. Well, I guess while we wait, how is everyone's finals going? 5 people, nice. People are starting to trickle in. Oh man. Nice. There's a bit of a delay, I think, from whenever you type stuff to when I see them. And then from whenever I say them to whenever you hear them. But yeah, this is fun. I definitely wish we were doing this in person. 7 people. Nice. Now the crowds are coming. Okay. So yeah. So this is for Dr. Nourani, I think is how you say it. Yeah, probably Dr. Nourani. So Eric was able to get me a list of materials he said are going to be on the exam. First thing is Boolean Algebra. I'm going to kind of go through this a bit quickly. If you have any questions, throw them either in the chat in YouTube, or I guess I'll keep the whiteboard open on Discord. And if I see any questions there, I'll answer them also. So, oh, Eric says my finals are next week. I'm enjoying the silence before the storm now. That's right. Look, the thing is, when if you graduate, you have no idea what time of the year it is. So let me fix this up a little bit. But still very busy week. Yes. Yes, I have noticed that's been the trend with a lot of you college kids. All right, so the Boolean algebra. So cover some of the basics. I have my little helper here. My coworkers, they refer to him as the verification engineer Elton. My little debugger, as I call him. All right, so Boolean algebra. I'm assuming you're good with ands and ors and things like that, so I'm not going to cover them too hard, but I am going to cover the identities. So if you have x or 1, this is always equal to 1. If you have x or 0, it's always equal to x. All right, so if you or number with my engineer friend is sitting at the table, I'm just gonna knock some stuff off. So if you or something with a 1, it's always going to equal a 1. If you or something with a 0, it's always going to equal itself. So this looks like you have your OR gate. You're inputting x and 1. The output is always going to equal 1. Similarly, your OR gate. If you input x and 0, the output is always going to equal x. Okay. So, yeah, any questions on that? Again, I know it's going to be delayed, so I'm going to keep moving on, but if I see a question in the YouTube chat or the Discord on the whiteboard, I'll go back. But I'm just going to keep moving on. Next thing would be the ands. So if you have and so if you and an x with a 1, the output is going to equal x. If you and anything with a 0, it's going to equal 0. So what that means is if you and 1 with some unknown value, it's going to equal whatever that unknown value is. And if you and a 0 with some unknown value, it's always going to equal 0. All right, so those are the 4 basic Boolean identities. Then we get into more tricky ones. Again, any questions, drop them in this chat or in the whiteboard. I'll run back and cover them. But I don't want to wait for a delay every time. So, yeah. Next one we'll cover the distributive ones first, or next. So if you have C and with A or B, this is equal to a C or a B. There's an acronym for you, but we'll move on. And yeah. Oh wow, viewers say it's down to 3. That's weird. Okay. The next one is if we have C or A and with B, that's equal to C or A and with C or B. So what this means is that the OR is also distributive across ANDs. I hate it just as much as you do, but it works in the digital world. So we have that because OR is on the same level of or hierarchy as an AND would be. Yeah. All right, so again, if you have any questions, drop them in the chats. I'm still not seeing anything in either, so I'll keep moving. Look at De Morgan's law. So De Morgan's law, let's see. I don't think, has Dr. Dodge been retired long enough for you all to? AC or BC star star? Oh, did I not write that? Yes, what Eric just typed. What I was trying to say is that the C gets distributed across the A or B. Yeah, I just realized I wrote AC or AB, and that would be totally wrong. So yes, as Eric just wrote, if you had C and with A or B, it would equal AC or BC. Yes, this wouldn't be AB. Yeah, I wish I could blame that on Rust, but I just blamed that on a long day at work. Yes, thank you, Eric. So De Morgan's law, if any of you had Dr. Dodge, he always liked to say break the line, change the sign. That works for 2 inputs. There's a more generalized De Morgan's law, but for this class, that's good enough. Break the line, change the sign. So what that means is if you have A, B, or A, B, NORD, so or NANDed together. So if you have a NAND gate with A and B as your inputs, what we're saying is that this is equal to, first thing you do is you break the lines. So this would be A naught, B naught. So we broke this line and then we changed the sign to an OR. So what that looks like is we had this, so we broke the line, change the sign. So what this would look like is you would have an OR gate as well as A and B being inverted going into that OR gate. All right, so that's De Morgan's law. Or that's one of De Morgan's laws, I guess you could say. The other one would be if you have A NORD with B. this would equal to, so if you start with A NORed with B, so if you broke the line and you change the sign, so, and basically. So what this looks like as a circuit would be A, B, being NOR together, would turn into, you'd have an AND gate with inverters going in. So A and B get inverted at the input to the AND gate, and then your output's the same as just a regular NOR. Thank you, Zygon. Did I say that right? Zygon? Zegon? I just want to make like a let's let Zygons be Zygons pun, but I don't know if I'm going to say it wrong, but thank you. All right, so De Morgan's law. It's more visual if you get into the like the actual circuit design of a logic gate, like with all the transistors and stuff. De Morgan's law becomes a lot more clear in the classes, but a question they like to ask a lot involves knowing some identities with an XOR. So if you have A XORed with a 0, this is going to equal A. If you have A XORed with a 1, it's going to equal A naught. So you can think of an XOR as a conditional inverter. So yeah, so if I look at my XOR truth table, let's say it's got two inputs A, B, and then the output A XOR B. So 0, 1. Okay, so if I consider this to be constant, so if I break this up, this is as if I'm XORing B with some constant 0, and the bottom half is as if I'm XORing a B or some B with a constant 1. So this is my output, right? We'll notice that in the top half, the output directly matches B, and the bottom half, the output is opposite of B. So that means if I XOR with a 0, my output will be whatever the other input was. And if I XOR with a 1, the output will be inverted of what the input was. So that's like the other identity that no one really talks about much, but it's a thing. So we'll cover it. Yeah, so I think that's about good on the identities. If anyone has another identity, drop them in the chat, but I think that's all of them, and for the most part you can derive these somewhat quickly, so we'll move on. How many people got the chat? 4? That number just keeps bouncing around, which I don't get, because I know that one of them is me, the other one's Eric. So I guess the other two are Zygon and Neil. I'm just assuming that people are going to watch this in the future, and they're going to have all sorts of questions, and they're not going to be able to ask them, because it's not live. But that's fine. All right, so next thing on his list was circuit optimization. So I think K-maps when I think of that. So real quick, I also know that later on I'm going to need a sequence. So if someone in the chat can drop like a 4-bit sequence, that'd be great. Just, some 4-bit combination of zeros and ones. Just drop that in the chat. And I'll make up a thing for a K-map. So I'll do in the K-map f of A, B, C, D is equal to sum of minterms 0, 2, 4, 5, 7, 13, and 15. And don't cares at let's see, 8 and 11. Okay, so I'm just gonna just make up some numbers and do a K-map for it. First thing to note, it's got 4 inputs, so we're gonna use a 4-input K-map. So 4-input K-map, I'm going to kind of gloss over some parts of the K-map because I'm assuming that you've done these ad nauseum at this point. So yeah, we'll just keep moving on. Okay, so we have A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0. All right, so I have my ones at 0, 2, 4, 5, 7. So 0, 1, 2, 3, 4, 5, 6, 7, and then 13, 15. So 8, 9, 10, 11, 12, 13, 14, 15. Okay, I also have don't cares at 8 and 11, which is there, 8, 10, and there. Cool. Okay. So first thing to do is look for the biggest possible groups. Oh. Okay, so Zygon gave me 4 choices, or he gave me 5 choices? 5 choices. And then Neil gave me 1 choice. Nice. I will go with the, I like the 1, 0, 1, 1. Yeah. Yeah, I like the 1, 0, 1, 1 for the sequence detector. So just put that here somewhere so I don't forget it. All right. So whenever we get to the sequence detector, we'll use that number. I didn't realize there was going to be a delay when I made this, so yeah, I don't really want to wait for a sequence whenever we got there. Okay, so first thing to do is we look for the biggest possible groups. As you can see, there's 16 blocks. So do we have group 16? If this were in person, you could answer quickly. You would all say no, but you gotta wait like 30 seconds for it. So I'm just gonna tell you, no, there's no group 16 here. Next, we look for a group of 8. So don't have a group of 8. Nope, no groups of 8. If this were a 1 or an X here, then we'd have a group of 4, or that'd be 1 group of 4, but it's not. So we only have 1 group of 4, and that's this group in the middle. Okay, so no other groups of 4. If we had like something here, that'd be group of 4. If we had something here, we'd have another group of 4. But that's the best we can do. So next thing is we look for group of 2, and we had groups of 2. So we have this one here. So that's a group of 2, and then we also have the one that wraps around the side. So we have this group of 2. So when we write our function, and then I should also mention, we didn't circle the x's, but that's fine, we didn't really have to. That's why they're called don't cares, is we don't really care if they're 1 or 0. They just don't matter to us. So, yeah, so when we write our function, first we'll look at this big group here. So that big group, in terms of A, B, C, and D, we look at what stays constant. So the term on the right, the B term, is 1 in both of these. So that first big group of 4 can be written with B. And then also the term on the right here, which is the D term, is also 1 the whole time. So this big group of 4 can be written as BD. The next thing would be, we'll just do this group of 2 here. So what stays constant is A stays 0, C stays 0, and D stays 0. So A naught, C naught, D naught. It'd be the group of 2 that goes vertical here. And the group that wraps around, we have A, B, and D are all 0. So this would be A naught, B naught, D naught. Okay, so that's your minimized sum of min-term problem right there. Yeah. So let's see, the next thing you might be asked is product of max terms. So let me make sure there's nothing in the chat. Nope. Cool. So let me erase this. Let's kind of start over. Let's see. So I'm going to rewrite the K-map. K-map again, put the 1s. I think this was everything. So I had, yeah, that's everything. Okay, so this time I'm going to focus on the zeros, which are everywhere that we didn't put a 1 or an x. And then get to grouping. So first thing is always we look for the groups of 16. There's no groups of 16 among the zeros. So we'll look for groups of 8 next. Also, no groups of 8. Now groups of 4, we got a few of them. We have a few of them. So, and they all wrap around. I did not plan on that, but that's kind of nice, I guess. So first group of 4 I see, let me do this in purple, I guess. I'm trying to pick colors that kind of show up darker. So first group of 4 I see is the one that wraps around like this. Let's see, I've also got one that goes around the top and the bottom. And then I've also got this one along the bottom. However, I'm not going to circle it because it's already covered by other circles. So you don't need to do that. Notice I did include x's in here. That's fine, but they're called don't cares because we don't care if they're 1 or 0. So whenever we make groups, we can use an x to make a bigger group, but we won't just circle an x, just to circle an x. And there's no way to get this into a group of 4, so it's just going to have to be a group of 2. No, I did not just make it its own because it's always going to actually be more efficient to have it in a group or have it in a bigger group than a smaller group. So since it can be in a group of 2, we'll put it in a group of 2 instead of just circling it by itself. And the same rule applies for the SOP form. Let's see, 6 people, so no questions, cool. So now we'll start looking at what these groups actually are. The first one we'll look at is these, the one that wraps around the sides down here at the bottom. What stays constant is A is always 1 and D is always 0. So since we're doing product and max terms, there's some tricks here. If anyone wants to see the derivation of why we do it this way, put it in the chat, I'll do it. But if this is second nature to all of you, I'm not going to waste time doing this whenever we can move on to other things. So, yeah, so A is always 1, so we call that A naught. And then D is always 0, so we call that D. Okay, so that's the first big group that goes around the sides. The next one I'm going to do is the one that wraps around the top and the bottom. So it looks like B is always 0 and D is always 1. So B or D naught. All right. So those were the 2 groups of 4 that we had. And the next one is going to be this group of 2, where B is always 1, C is always 1, D is always 0. So this would be B naught or C naught or D. Okay, notice all of these inputs are inverted from what the group said that they would be. And that comes from the fact of knowing that we're circling zeros instead of ones. And de Morgan's law kind of takes care of the rest. So if you want to get to this the long way, you can circle all of these and treat it like the last one where you write it in SOP form, but knowing that this would be F naught, and then invert everything, do de Morgan's law like 2 or 3 times, and you'll get to this. Okay, so that's the quick brushing over derivation. If you have any questions about this, drop them in the chat. I'll go back and cover it. Or if you're watching this recorded, just tell someone in the put in the tutoring chat on Discord that you don't understand that, and someone will probably help you. I don't know. I'm not going to talk for everyone, but I would help. All right. Next one on the list is combinational components. That sounds like logic gates to me. Oh. Yeah, I understand how POS work. Good. You know why we call it POS, right? It's not because product of sums. I mean, it's technically it's product of sums, but that's not what we were saying. So next on my list is combinational components. When I see that, I just think ands, ors, XORs, inverters. The inverted version of all those things. I don't know. If there's anything you want me to cover in there, let me know. I'll go back to it. Oh, I guess also tri-state stuff. If you want me to cover tri-state, I'll do that too. But I'm probably just going to move on. If your professor didn't talk about tri-state at all, it's not going to be on the test, or it should be on the test, but I'm not going to talk for him. So we'll move on to sequential components, which I think are just flops. My habit of doing all this in person is I was about to ask you if it was okay if I erased this, as if we were in person. Yeah. If you were not okay with me erasing it, rewind. So the next thing is different types of flops or flip-flops. We call them flops in the industry. Don't mean to be that guy, but we do. So the two main ones are D flip-flop. So there's 4 pins that are always on the D flip-flop. Sometimes they put a set or a reset on there, but it's rare that they do that in these classes. So basically what you need to know is that this is your clock. Depending on your professor, he might say it's always triggers on the rising edge or the falling edge. Can you cover implication table or other ways to simplify an FSM? Yes, I'm covering that later on when I do the FSMs. If you need more information on that, my YouTube channel, I actually have a YouTube channel, has a video all about FSMs and minimizing them. Someone is calling me. I'm sorry that that's right next to the microphone. I have it there to watch the chat since I don't want to use my computer for that. But yeah, someone was calling me and my phone's right next to the microphone, so my bad. So yeah, I will cover FSM or implication table minimization. However, if you want more, I have an entire YouTube video dedicated to those, as well as I want to say several, but I know it's at least one completely worked out example of an implication table. Okay, thank you. Cool. I just realized I was talking about that long enough for it to reach back to you and you to comment again. My bad. I'll move on. This is weird not talking to anyone except for a chat. And yeah. Okay. So types of flops, we have the D flip-flop. Way to remember this, D stands for data, which means that whatever triggering edge you have, the output Q is going to capture whatever's at the input D, data. So, for example, if this is your D to data, this is your clock, this would be your Q. So if I make some clock signal, enough, okay, so if I look at every triggering edge, so I'm just going to put little dotted lines on all the triggering edges. We're just going to say this clock or this flop is triggered on rising edges. Again, it could be either way. I've seen either way. At my work, it's been done. So, Jeremy's YouTube. Oh, I guess Eric's going to share my YouTube channel. Thank you, Eric. Thank you. Yeah, so we look at every triggering edge, and whatever the output is, that becomes our clock. So at first it's unknown, and then at this point we know it's 0. So we go down to 0. I'm just going to put this all the way down. So 0, at the next rising edge, our D is high, so we will go high till at least the next clock edge. Then we'll look at D again, it's still high. We look at the next clock edge, D is low, so we go low. D is low still, and D is low still. So the thing to remember is that on the only time that your Q actually looks at the input is on the triggering edge, which I said was going to be rising edge. Your professor might say it's falling edge. I can almost guarantee you can just ask the professor if it's going to be rising edge or falling edge, because that's not supposed to be the hard part of the problem. It's just supposed to see, do you know that a D flip-flop, or flip-flops in general really, only sample on the triggering edge of a clock. So yeah, and that's kind of the big difference between flip-flops and latches. So latches are supposed to be opaque in that they look at the input during periods of time, right? So a latch, yeah. Whereas a flip-flop, it only looks at it at a specific time. Yeah. So the next one I'll look at is, and I'm assuming there's no more questions with the D flip-flop. I'm just gonna move on. If there is any, I'll go back. But I don't want to wait for you guys to ask a question and for it to get through all the delays to get to me. So I'm gonna look at the T flip-flop. It's the other type. And the T stands for toggle. My cat just knocked a bunch of screws off my table. That's great. All right, so the important thing to know is that the T input tells you when to toggle the input or leave it the same. So if your T is low, you toggle it. If your T is high, you stay the same. For this one, I'm just going to say the initial value is a 0 on Q. So this is my input T. And I'm going to say the initial value is 0 at Q. And I'm going to keep the same input T, or the same input on the clock and the T. I'm just going to show you how we do it differently now. You do have to know an initial value for Q. Otherwise, you're toggling from something you didn't know before. So the opposite of something you don't know is also something you don't know. So we're going to assume that Q starts at 0. And then at the next clock edge, T is 0, so we stay the same. The next clock edge, T is high, so we toggle. At the next clock edge, T is high, so we toggle again. Next clock edge, it's low, so we stay the same. It's low, so we stay the same. And it's low, so we stay the same. All right. So they're fairly straightforward. It's just you have to remember what the T's and the D's stand for. The T flip-flops are going to be used more for like counters. So if you're building a counter, you're probably going to use a T flip-flop, but you can use the D flip-flop if you want to. Similarly, for a D flip-flop, they're mostly going to be used for registers. I mean, you could technically use a T flip-flop if you wanted to, but you're just going to have an easier time building a counter with a T flip-flop and a register with a D flip-flop. That's just kind of how it's always going to work. So here that covers the initial stuff, and then I think they said we're going to be in the main part of the test itself, is going to be let's see, your design of sequential circuits is my next thing. So the two things I planned for this was design a counter and design a sequence detector. So the counter like I said, it's going to be easier if you build it with T flip-flops than with D flip-flops. So if you just kind of look at the sequence that you should see in a counter, you should see it going 0, 0, 0 to 0, 0, 1 to 0, 1, 0, 0, 1, 1 to 1, 0, 0 to 1, 0, 1, 1, 1, 0, and 1, 1, 1. I'm just going to do 3 bits because anything more than that, and it's just lipstick on a pig at that point. You're making it harder than it needs to be. So the trick to the counter is that the next bit increments every time all the previous bits are 1. So we'll notice that this bit here increments every time the 1's place is a 1. And then this the 4's place is going to flip every time the 2's and the 1's place are both 1. So whenever both these are 1, this is going to toggle the next round. And whenever you wrap back around, since these two are high, you're going back to the top, and this is going to toggle. So that's kind of the main thing to get from all this, or at least to understand about the sequence. So since we're toggling, we're going to have 3 T flip-flops. Okay. The input to this first one is always going to be 1, because every time that you clock it in, your least significant bit is going to be toggling. This output is going to go into the next T. However, I can make it more general and say that I'm ANDing it with the result of the previous input, which is a 1. So remember our identities from earlier, if you AND anything with a 1, you just get the original value back out. But the important thing to remember is that this next flip-flop, if we AND it with the result of this one, we know that this is going to be a 1 whenever the output of the previous bits are going to be a 1. So basically what this says is that the only time this is going to be a 1 is whenever every previous bit is a 1. The only time that this is going to be a 1 is whenever this is a 1, as well as all the previous bits, which means every other bit is going to be 1. So if you want to extend this on to infinity, you just need to copy this block right here and just keep pasting it on. So yeah, this is how you make your counter. This is going to be where you take your outputs from. So this is going to be your least significant bit. This is going to be your most significant bit. That's your middle bit, which we don't give a name to, just like middle children. Sorry, middle children out there. But yeah, so your least significant bit is going to toggle every time. Your middle bit is going to toggle as long as the least significant bit is a 1. Your most significant bit is going to toggle as long as both, or all of your middle bits, just the 1 in this case, as well as the least significant bit, are all 1s. So that's basically how the counter works. It's kind of straightforward, but you know, we build it with T flip-flops just because it's more based around when to change rather than what the actual data is. Alright, next thing we have is a sequence detector. And I'm going to build this one like an FSM. And if there are any questions about any of this stuff, leave them in the chat. I'll run back. But if not, I'll just keep moving. So far, I haven't seen many questions. So 1011, that was our sequence. Grab a check real fast. We're making pretty good time. It's barely been an hour. Well, hasn't been an hour yet, but nice. So yeah, first thing we do is we solve for our success state in a finite state machine. So we have some state that we start in, which I'd like to name A, that we start in. The output of A is 0. So I like to say X is my output and B is my input. So alright. So basically what I'm going to do is I'm going to get to this state. Once I detect this sequence, I'm going to output a 1 for 1 cycle and then start over basically. So first thing I always do is I find my success state, which looks like inputting first a 1, then a 0, can't tell if I'm going to run out of room that way or not. I think I'm going to circle back around. Then a 1, and then oops, this is the final one, my bad. And a 1. So notice how we got there was inputting a 1, a 0, a 1, and then a 1. And at this point, we're about halfway done, believe it or not. So now we need to go through and find out what happens when we input the wrong thing. So if we were at state A here, and if you input a 0, well, we got to state A by either starting or starting over the sequence. So if you input a 0, then you're going to actually stay at A. And then we know if we input a 1 while we're at A, we're going to move to state B. If you're at state B and you input a 1, you have to remember how we got to state B. How we got there was by inputting the first 1. So what we know we have at B was 1, and now we're here. So if you input another 1, where we're at in the sequence is we're still here at the first 1. So we're actually going to stay at state B because we're at 1 and we're just looking to start the sequence over again because we're looking for 0, 1, 1 still. So we're still looking for 0. This will just act as our first 1. Sorry, I kind of live right by the fire station, so you'll probably hear some weird noises at my apartment. I live by an airport, a fire station. There's a road right below me. So, yeah. So if you get a 1, you're actually going to stay at state B. All right. I'm going to just periodically check. If you have any questions on any of these states, let me know. I'll explain them more. But I'm going to keep moving, so I'm not waiting every time. If you're at state C, so notice you got to state C by inputting a 0. So if you input a 1, we know we go to state D, but if you input a second 0 in a row, that's no part of the sequence. So if you input a 0 when you're at state C, you go all the way back to state A. I should also mention I'm building this like a more machine, in that the states are only dependent on the current, or the output is only dependent on the current state. If I were building it like a melee, then the output would also depend on the current input. That might be a question that they ask. Eric says, haha, I'm assuming that was about the fire station. I think that's the only funny thing I've said recently. But yeah, I hate this delay. It is so bad because I don't know which of my jokes are landing and which of you guys are just, you know, face palming to. But yeah, so state C, if you inputted 0, that means you've inputted 2 zeros in a row. So we're starting the sequence back over. And if you input a 1, that means you've inputted a 1, 0, 1 at that point. So let's look at what happens when you're at state D. So at state D, you've inputted, to get to state D, you've inputted 1, 0, 1 to get there. So far you don't know what you've done before, but you know you've done 1, 0, 1, and now you're here. And if you put a 1, obviously you finish the sequence, you go to state E. But if you input a 0, you don't exactly start over like you would have at state C, for example. Because at state C, you inputted 2 zeros together, and 2 zeros are no part of the sequence. However, if you input a 0, this part looks a lot like the start of it, right? This 1, 0. And so suddenly you're back to state B, actually, because B is where you've, or I'm sorry. No, you're back to state C. I don't know what I was thinking. There was a trick there to prevent me from ever making that mistake, and I'll show you that in a second. But I made it anyways, and I caught it really fast. But in the chat, you're gonna let me have it in like 5 seconds, so I might just turn it off. But yeah, so if you input a 1, 0, you go back to state C, because that means that you've inputted a 1 and a 0, which looks a lot like having 1, 0. So inputting 1, 0, you're back to state C looking for the third element of your sequence. And yeah, so now we should be done with D. So the only one left to look at is state E, which is where you've inputted 1, 0, 1, 1 to get to state E. Okay, so for state E, you've inputted, you don't know what you've done before, but you know the last 4 have been 1, 0, 1, 1. All right, and now you're looking at what you get here. So if you input a 1, so if you input a 1, we need to look at this sequence and see how much of it we can overlap with this one, which looks to just be the first 1. So if you input a 1, that means that you've got the first 1 of your sequence. All right, that's the most that you can have out of it. So inputting a 1 will send you back to state B, because state B is the state where you've had the first 1. If you input a 0, again, we do the thing where we look at how much of this we can overlap with this. It looks like we can overlap these first two states. So that looks like having 1, 0, right? Because that means that the last 2 here were, 1, 0. So inputting a 0 when we're at state E means that we go back to state C. And to avoid things from getting too congested in here, I'm going to just draw this one all the way around. I call it like that. All right. So now let's look at Let's look at the two things to check always for whenever you think you're done with should have a path when the input is 0. Yes. I assume it's delayed. But yes, I'm just assuming I've covered that at this point. So that comment probably came before it showed on the screen. So first thing I look for is exclusiveness, and the second thing I look for is completeness. Actually, you can look for both. It doesn't matter what order you check them in. Exclusiveness means that at every state, sitting in a single input should lead to exactly one other state, or it should have one destination for every input. So since I have basically one input b, it's 1 bit long, so b can only be either 0 or 1. We don't care about x. We don't consider what if we send in an unknown value. No, we just care if it's 0 or 1. Those are the two states that we care about. So we look at state A, and we look. If I input a 0, where do I go? I stay back to state A. And there's no other place I can go if I input a 0. If I input a 1, where do I go? I go straight to state B. So I go to B and no other place. There's no arrows other than this one that has a 1 over it. Just as there's no arrows other than this one going out of A that has a 0 over it. So, yeah, so I will say state A is exclusive. I'll also say it's complete. Complete means that there's no input you can throw at it where it doesn't know where to go, or it has no destination. So the only two possible inputs I can throw at that are 0 or 1. And in both cases, it has one place to go, or has at least one place to go and only one place to go. And so the at least part means it's complete. The only one place to go means it's exclusive. And you can do the same thing for every single one of these states. For example, B, if you input a 1, it's going to stay at B, no questions about it. If you input a 0, it's going to go to C, no questions about it. All right, so you can follow the same pattern with the rest of these states. They are all exclusive, they're all complete. Another thing is, earlier, I drew an arrow. I don't remember where I drew it, but I said I should have seen that quicker because there's a trick with sequence detectors where every arrow going into a state has to have the same input on it. For example, if I look at state A, the only arrows that go into A have a 0 over it. So there's this arrow, and there's that arrow. And there's technically the start arrow, but that's just telling you where to start. That's not really an input, per se. If I look at B, I have this arrow, and that one, and they all have 1s over it. So sequence detectors, the input that gets you to that sequence detector is always going to be the same. Just kind of a trick for that. But I did have an arrow, I think it was from D. I drew it to B whenever it should have been this one to C. And I was drawing an arrow with a 0. And I should have seen that all the arrows going into B are 1s, so there's no way I can have an arrow with a 0 going into B. But yeah, so that's the other trick with sequence detectors. I'm sure that they can come up with some weird example, but it's not going to be a sequence detector that breaks that rule of the arrows going in. And I will say professors love sequence detector questions because they're kind of easy to grade. So next thing I have on here is implement the sequence detector into a finite state machine schematic. So we're going to build a, so this is our state diagram. We're going to build the truth table with it. So I'm gonna just curious if any of you don't have it written down, just go ahead and write down the states or the state diagram. I'm not sure, since I don't see any of you, I don't know if any of you are writing it down, but yeah. I'm gonna just flip this over. Oh, my cat says you're all living in a simulation, so silly Elton. Funny cat. I don't know where he got off to. All right, so the states we had were, okay, how many states we had? We had A, B, C, D, E, 5 states. So you can represent that, like you'll need 3 bits to represent that. So my state register, I'm gonna call it S2, S1, S0. That's my state register. This is gonna be my input B. This is gonna be my what should I do next? I'll do my next state. So the next state, I'll call it N2, N1, N0. All right. And my output will be X. So we'll have 0, 1, 0, 1. I need to make this smaller. I can already tell I'm more than halfway there. I'm putting dividing lines on every group of 0 and 1. I'll show you why in a second. I also don't really need most of the bottom half, but I do barely need it. I can't tell what you all are replying that to. I'm assuming it's to Elton's message. We are living in a simulation, though. Just, you know, it's known. It's very widely known. All right, so now we fill up the current state. So S2 through S0, that's all for the current state. And the outputs are, or we're going to encode them just in binary. So 0, 0, 1, 1, 0, 1. 0, 0, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4. All right, and this is going to correspond to state A, B, C, D, and E. And then these are all states that don't really exist. So for all of these, they're all just going to be don't care on both the output as well as the next state. Because they themselves don't exist. So we don't care what the next state's going to be, because if we built this right, they're never going to get there. All right. So first thing to look at is if I'm at state A and I input a 0 and a 1, where do I go? So looking at state A, if you input a 0, you stay at A. If you input a 1, you go to B. Okay, so if you're at state A, you input a 0, you stay at A, which means we've encoded state A to be 0, 0, 0. If I input a 1, I go to state B, 0, or which is encoded as 0, 0, 1. Right? And it's a similar process for state B. If I input a 0, I go to C. If I input a 1, I stay at B. So if I input a 0, I go to C, which is 0, 1, 0. If you have any questions on how I'm building this, let me know in the chat. I'll go back and cover one of them. But I'm going to kind of breeze through this a bit. The next thing I have is state B and putting a 1, which we stay at B for. So 0, 0, 1. If I input, or if I'm at C, let me look what happens when I'm at C. If I input a 0, I go back to A. If I input a 1, I go down to D. So inputting a 0, I go back to A. So A is 0, 0, 0. If I input a 1, I go down to D, which is 0, 1, 1. Look at state D. If I input a 0, I go back to C. If I input a 1, I go to E. So 0 goes to C. C is 0, 1, 0. E is 1, 0, 0. Next I look at E. If I input a 0, I go back to C. If I input a 1, I go to B. So a 0 sends me back to C, which is 0, 1, 0. And a 1 sends me to B, which is 0, 0, 1. Now the only column left is the output. All right, and the output is tied directly to the state, the current state, because again, I said I'm building a more, not a melee. So, yeah, my output's tied to the current state. So in every state except for E, it's going to be 0, and in E, it's going to be 1. So we've got 0, 0, 0, 0, 0, 0, 0, 0, and then I'm at E, and it's 1, 1. All right, so there's my truth table. And yeah, so now we get to the fun part where we have to solve for what this actually is. I'm gonna grab a drink. Normally during this part, if this was in person, everyone would be writing this down a lot, but I know you guys can pause it whenever you want, so, or rewatch it. So while everyone would be writing, I'd be taking a drink at this point. All right, so we'll start minimizing. At this point, I'm going to erase this side. And I'm going to start solving for the variables, the logic part of the variables. And I'm going to consider, I'm going to solve for the combinational logic part of this, and I'm going to consider these 4 as the input, and these 4 are the different outputs I'm solving for. All right. Yeah. So first output I'll solve for is N2. So N2, I have form that came out. All right, inputs are S1, S2, S0, and B. S2, S1, S0, and B. Cool. Wow, 5 viewers. Look at us go. Okay, filling this out. We have a 1 down here at, this is going to be number 7. So there's place number 7. And then I have x's from 1, 0, 1, from 10 onwards. So 8, 9, 10. So from here onwards. All right. So I can write this as, circle that group up together. So yeah, I'm going to put this over here. N2 is equal to, and I write this down, I have S1 and with S0 and B. S1, S0, B. So that's N2. Next I'll look at N1, or actually all these x's are going to stay where they're at. I'm sure we're a better way to erase selectively. I don't have any of those fancy tablets that everyone else has. But you don't have to pity me, I have a whiteboard. Alright. So this is going to be N1. So N1, we have it, that's going to be place 2, 5, 6, 8. So 2, 5, 6, and 8. So 2, 5, 6, and 8. Okay, so we have a group of 4 here, we have a group of 4 here, and a group of 2 here. Okay. So N1 is going to equal to, this is going to be S2 and with B naught. This is going to be S0 B naught. And this is going to be S1 S0 naught B. Cool. I'm still not seeing any questions, so I will keep going. I'm going to redraw this because it's going to get kind of messy if I don't. So this is going to be N0 next. And again, the N stand for next. I want to go back and reiterate that we're solving for our next states at this point. Just in case I haven't said that recently, it's very important to remember what you're actually solving for. Otherwise, what's the point? If you don't know why you're doing anything, why do it? 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0. Got S2, S1, S0, B. Remember. Looks like there is a question. Oh, never mind. Nope, I'm just stupid. That was in the tutoring chat. I also realized in the past I hadn't put that X on midterm 11. We'll just hope it doesn't come back. I don't think it's really going to matter. It might just mean that we didn't minimize all the way, but there is supposed to be an X there. Okay, in one we have 1, 3, 5, 9. 1, 3, 5, 9. Okay. So 1, 3, 5, 9. Nice. So we've got this group of 4. And we've got this group of 4. Notice I did this group of 4 because this one was still out there. I could have put in a group of 2, I could have put it by itself, but I made a bigger group, which is important because you save transistors that way. And I don't know if this class covers that or not, but bigger groups mean fewer transistors. That's important. All right, so in 0, so this big group is going to be S0 not B. And then this group before that wraps around is going to be S1 not B. All right, and the only one left is the actual output. Which I could put into a K-map, but I kind of already know that I can just make it equal to whenever this S2 is high. Because notice S1, so it's X for the bottom half, and then S1, which also lines up with what E is, or this this whole group right here. So these, I don't want to say perfectly line up because they are don't cares, but don't cares count. You'll end up grouping them anyway, so I'm not going to make the K-map for it. So I'm going to say X equals to S2. And I will start building my FSM, the actual circuit. So the main parts of the finite state machine are the combo logic, the state register, we've got the input, we've got the output, all right, and you've got some feedback going on. Exactly, you have 3 groups of feedback going on, or 3 wires of feedback going on. Make sure there's no questions. If there's something in here, let me make sure it's not related to this. It is not. Cool. So these are going to be related to the next states that feeds back. And the state register is going to feed back into the combo logic, the current state. So it's going to be S2, S1, and S0. So it'll be N2, N1, N0. And just make sure this lines up. So this can be N0, N1, N2. All right. Now I need to, the only thing missing is this big white box here. So let's see, N2 is just one big 3-input AND gate. I will do N2 in blue. So N2 is this big 3-input AND gate. Which inputs which has the input as well as S1 and S0. All right. N2 is going to be a group of 3 AND gates. So we've got 3 AND gates that all get OR together and create N1. All right, so we have B, which needs to go to all of them. Be inverted on 2. This is kind of cluttered up, but I think as long as I say what I'm doing, you can kind of understand it. It would be a lot easier if I wasn't doing this on such a small whiteboard, but I am. So we'll go with it. Okay, that's related to the tutoring. Okay, I was just looking at the whiteboard chat and someone posted some problems, but it's for some other tutoring going on. Nice. And then this goes straight to here. So S2 and with B, so I need to grab S2 and put it there. Next I need S0, just this line here. And then I need S1, S0 not. So this and here, I'm ending the input B with the inverted S0. So I take S0, I invert it on the input of this AND gate. And then this one, I'm taking S1 and just passing straight into the AND gate. For this AND gate, I'm inverting the input. So this inverter bubble goes to the line that comes from the input. This line goes to S0. No, it goes to, did I count that right? Yeah. Yeah, it goes to S0. And then this AND gate, I'm taking S2 and I'm also inverting the input B and ANDing those together. And the result of all those AND gates I'm putting into the OR gate, which goes to my next state, which feeds back in. You get the picture. Let's see, the next one I have is my next state 0, which is the result of 2 AND gates that get ORed together. Okay, so B input gets passed directly into both. Then both of them take the inverted versions of So this one is going to have the inverted S0 ended with the input B. This one's have the inverted S1 as well as the input B. The result of those get ORed together into the OR gate, which gets passed into the next state, which gets put back into the state register. Now the only thing left is the output X is equal to S2, which is the easy one. Yeah. All right. So here's your finite state machine in a circuit. I haven't seen any questions yet about all this stuff, but I guess I can move on. We've got about 30 minutes left in the official time, but I don't mind staying a bit late if anyone has more questions at the end. Next thing I have on the list is arithmetic circuits. Again, I'll do the state minimization thing later with the implication table. But yeah, Okay, so arithmetic circuits, I just think of adder, subtractor, multiplier, and divider. I'm going to cover the adder, subtractor, and then I'll do the multiplier or divider after that. If your professor didn't talk about dividers at all, let me know in the chat and I just won't cover it. But I don't know if that's something covered by every professor or it's just covered by mine. Okay. So the adder, subtractor, or the adder first, I'll cover. What we get is, or we consider just adding two numbers together. So A, if I input A and B, so if I'm adding A with B, so A plus B is going to be, so if I have 0 plus 0, that's going to be 0. Just realizing I need to do it over here. So 0 plus 0 is going to equal 0. 0 plus 1 is going to equal 1. 1 plus 0 is going to equal 1. 1 plus 1 is going to equal 0, but with a carry of 1. So I need a carry input. I'm going to call it carry out, because we need 0 in every other case. So this is your truth table for a half adder. All right, this should be fairly straightforward. I'll jack it up, I got one in here. Can't tell if it's about to rain or not, but oh well. So this is your half adder circuit. The difference between half adder and full adder is with full adder you consider a carry in. So you have a third input, carry in. I'm just going to basically duplicate the circuit and basically just double everything again. So 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. All right, the top half basically stays the same. 0 plus 0 plus 0 is equal to 0. 0 plus 0 plus 1 is equal to 1. 0 plus 1 plus 0 is equal to 1. 0 plus 1 plus 1 is equal to 2. 1 plus 0 plus 0. Now we start adding is 0, 1. 1 plus 0 plus 1 is going to be 2. 1 plus 1 plus 0 is going to be 2. 1 plus 1 plus 1 is going to equal 3. All right, so there's your full adder. Straightforward. Pretty much any time you see it, it's going to be denoted as a box. It just has the initials for Fat Albert. I'm just kidding. Full adder. AB. I think we do. Yeah, it kind of just depends on where you put it, but it's gonna be like A, B, carry in, and you'll have the outputs carry out with sum, like S for sum. I don't like to use the variable S because sometimes it looks like a 5, but it kind of just works for this case. Plus, if we're doing everything binary, we shouldn't ever see an actual 5, so it won't really matter. But yeah, so that's what your full adder will look like, and then in like an actual circuit. So this is fairly straightforward. If you have any questions, let me know in the chat as always. I'll run back and grab and cover them. If not, I will move on. I've seen very few questions. So, and I guess I'm just that good. I'll go with that. All right. So if I wanted a 4-bit full adder, how would I do that? Well, you would have 4 full adders. I think I went from on this side. All right, we have 4 full letters, and just A, B, carry, N, A, B, carry, N. All those people with tablets can do that copy paste stuff, but they haven't come out with that for whiteboard yet. New technology. All right, so in terms of internal circuit, every carry in will be tied to the previous carry out. The outputs will be probed from all the sums. This will be, if we're doing an actual just adder, this will be your final like MSB. This will be your LSB. And then the inputs will just come from the numbers themselves. And this initial carry in will be a 0. Again, we're just building an adder at this point. Let me double check. No questions anywhere, so I'll keep moving on. So yeah, so this would be like inputs A2. A3, B3, A2, B2, A1, B1, A0, B0. So if you were to add, I don't know, 3 plus 4. So if you were to say A equals 3, B equals 4. So if you put on the A line 3, so 0, 0, 1, 1. And on the B line you put 4, which should be 0, 1, 0, 0. And you fed that through. So 1 plus 0 would equal 1 with no carry. So this would be 0 here. So 1 plus 0 is also going to be 1 with no carry. Bring that around here. 0 plus 1 plus 0 would be, again, 1 with no carry. 0 plus 0 plus 0 be 0 with no carry. So your outputs, if you look at here, you have 0, 0, 1, 1, 1, which in binary gives you 7, which you should have expected. All right. One question, I don't know if it was this class, but I know when I took this, they loved asking this question on homeworks. And I think I saw it sometime this semester too, during one of the tutoring things, but I don't really remember. They kind of blend together. But what happens if you want to make a conditional subtractor? Well, you have to remember the identities I had with the XOR gates earlier, which is where if you XOR with a 0, you just pass the value through, but if you XOR with a 1, you invert the bit. Right? So, if you wanted to do that, I don't want to erase that yet. So, what we have to do there is I want to conditionally I want to have an extra input. I didn't mean to erase some of this. I want to have some extra input called S, where if it's 1, I subtract. If it's 0, I add. So the way I do that is, so some of this stays the same. I didn't mean to erase this. Is on every, so if S equals 1, subtract S equals 0, add, and I'll do A minus B. So B is the number I want to become negative. I realize I probably should have covered 2's complement. I'm just going to breeze over 2's complement. If you want me to do that, I'll do it, but I'll kind of just breeze over that for now. All right, so if I have an input S, I want to feed that into an XOR time every B. So B is going to be fed by an XOR gate. Where B gets XOR'd with S. All right, so if S is 1, B is going to get inverted. If S is 0, B is going to stay the same, just pass through. A just passes through no matter what. So A is always positive, B, sometimes we want to make it negative. And the first thing you have to do to make B negative is make it 0, or invert all the bits. Next thing you have to do to B to make it invert or negative is add 1 to it. And there's no pretty way to do that on the inputs. However, we have this convenient carry in. So when S is 1, I'm going to be carrying in a 1 that wasn't there before. So that's the same as adding 1, the add 1 part of the 2's complement. So if you remember 2's complement, you have to invert all the bits and then add 1 to get the negative number. So let me erase some of the values from before. So what happens if I want to do 5 minus 2, I guess. So if I want to do 5 minus 2, all right, so this means A equals 5, B equals 2, S equals 1. All right, so S is 1 because we're subtracting, B is 2 because the negative number is 2, and then A is 5 because 5. So S is 1, A is 5, which is 0, 1, 0, 1. B is 2, which is 0, 0, 1, 0. Okay. Make sure there's no questions. No questions from me. Everything's great so far. Good. I'm glad. Yeah, Eric, I'm glad you had no questions. Eric, you should be doing your VLSI stuff at this point. Oh, so it's an add subtract circuit, right? Yes, it is an add subtract circuit. That just popped up for me. So now you know what the delay is. That's how much delay I have. I just realized I should plug in my phone. It'd be really bad if this died because I have no other way of monitoring the chat. Okay. So, what am I doing now? Okay. Since S is 1, I'm XORing with a 1, which you remember from our identities earlier means I'm inverting. So this 0 becomes a 1, this 0 becomes a 1, this 1 becomes a 0, and this 0 becomes a 1. As well as, remember the subtract line, which means that this first carry in is also a 1. So, if I look at, I'm just going to write the A value closer to the flip-flop. So I'm just writing closer to the flip-flop so that it's already there. So if I look at this first flop, I've got, or the full header, I call them flops. It's been a long day. All right, so if I look at the first full header, I have 1 plus 1 plus 1, which is 3. So this 1 gets carried up to here. So we have 0 plus 0 plus 1. This 1 carries 0. 1 gets brought to, or the 0 gets brought to here. I have 1 plus 1 plus 0. It's going to be 2. So we have 0 carry a 1. And then this one here, we've got 0 plus 1 plus 1. Just carry out a 1. And we have a 0 there. All right. Now before, I had the MSB here. But whenever we have an adder subtractor, we don't care about that last carryout. Reason is because if you're subtracting, that's always going to be a 1. So, yeah. It only works if you have just an adder. But if you're using an adder subtractor, this last bit's always going to be a 1 because it just will. All right. So if I look at my values, I have 0, 0, 1, 1, which is 3, which we expected because 5 minus 2 equals 3. All right, so there's your adder subtractor. Yeah, it's somewhat straightforward. It just relies on you knowing the identity with the XORs, where it's a conditional inverter, but it's not too bad. Next thing I've got is multiplication. I'm actually going to just flip up the whiteboard. If I have multiplication, so if I have 0, 1, 1, 0. So this is equal to 6. And I said I want to multiply that by 2. It's not too hard to do. You just left shift by 1. So it's the same as with a left shift by 1. So if I left shift by 1, these two go over here. So we end up with 1, 1, 0, 0, which is equal to 12. All right, so multiplying by 2 is not too bad. If I wanted to multiply by 4, well, I have to left shift by 2. So if I multiply by 4, I have to left shift by 2. So I'm already up to this point. So this was after left shifting by 1. So if I left shift again, I end up with 1, 1, 0, 0, 0. So if I look at this, I have a 1 in the 16th place plus a 1 in the 8th place. So 16 plus 8 is going to equal 24, which 24 is equal to 4 times 6. So 4, I multiply by 4, so I left shifted by 2, gives us 24. Now what if I wanted to multiply by 3? Then things get a bit more complicated. So if you want to multiply by 3, you need to first left shift by 2, or here, I'll put it this way. 6 times 3 is equal to 6 times 2 plus 1, which is equal to 6 times 2 plus 6 times 1. This is your left shift by 1, and this is just passing the original value through, so left shift by 0. So in other words, I take the left shift by 1, which if you remember was 1, 1, 0, 0, add it with the original value 1, or 0, 1, 1, 0, add these together. So 1, 1, 0, 0 plus 0, 1, 0. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, carry a 1, 1 plus 1 is 0, carry a 1. So here we have a 1 in the 16th place plus a 1 in the 2's place. So 16 plus 2 is going to equal to 18, which is 3 times 6. Ooh, there's something in here. Will you carry will the carry out be sign bit, or it just doesn't matter? It doesn't matter. So that's a good question. And I think at the point where you're asking that, it was again, this is a bad thing about no direct feedback, or delayed feedback. I think the point you're asking that is after I did the adder subtractor, and I added two numbers together, and I found that that final carry out bit was a 1. So yeah, if that final carry out bit was a sign bit and it was a 1, that'd mean that I got a negative number when I did 5 minus 2. I know it's not a very good defense that, because my example would have been wrong if it were a sign bit. That's like a terrible defense, but that's the way I remember it, is that it would be wrong. But yeah, that last carry out just doesn't matter. I'm not sure if that answered your question or not. If it were a negative number, you would have ones padding out. So the output of the, right here, I'm going to flip over. This bit here is your sign bit at this point. Yeah, so this is your sign bit now. This bit, don't worry about it. It'll be 1 sometimes, but it's not gonna always be a 1. It's just not gonna be part of it. If it's a 0, that means that you're adding 2 pretty small numbers. If it's a 1, it could be a 1 if your answer is positive or negative. It usually is a 1 because you're subtracting. But yeah, it could also be a final carryout. It's very conditional, I guess. Like if you're adding some number that overflows that full adder itself, like if you're adding some numbers that result in a 5-bit number, then yeah, this will actually carry out, but you'll have to kind of assume that it's a bigger number than your circuit will allow. So in other words, you threw that's considered like an input that you wouldn't be allowed to throw into it. And I think that would only happen if at least if one of these were 1. But there are cases where you can overflow the 4-bit full adder. But you know, we just kind of hope we don't get to those. I hope that answered your question. If you have, okay, you said okay, thanks. Okay, I guess I answered it somewhere in the last however long the delay was. So we'll go back to the multiplier. All right, so next thing we need to talk about is shift registers. Shift registers we usually draw with a rectangle, and let's say we're doing left shifts. So if I were doing a left shift by 2, we'd draw it like this, and we'd have some bit with n going in, and then n plus 2 coming out. So this symbol we denote for a bus. It's like a bus of n wires going in, and then if we're going to left shift 2, we need to have at least n plus 2 coming out. But yeah, so let's talk about division real fast, or let's do a multiplication circuit real fast. So if I want a circuit that you input, so input a 4-bit number, output 6 times the input. So if I have this, so if I input a 4-bit number and I output 6 times that number. All right, so I have input x times 6 equals output. So x times 4 plus 2 equals out. So x times 2 squared plus x times 2 to the 1 equals out. So x left shift by 2 plus x left shift by 1 equals out. All right, so this is basically how your circuit's going to end up looking. So if I input x, and it's a 4-bit number, as I said before, I send this into a shift register, which is left shift 2, as well as a shift register, just left shift 1. All right, so the output of this will be 4 plus 2, so 6 wires long, or 6 wires wide. The output of this will be 4 plus 1, 5 wires wide. And these need to go into a full adder block. And the output of that full adder block needs to be one more than the biggest input. It should be 7 wires wide, and this will be your output. So what does this circuit do? Let me make sure there's no questions. Oh, okay. There's stuff. Got it. So 3 less significant is to the magnitude. Not quite the magnitude. Because your answer is going to be in 2's complement for that circuit. Did I hope I didn't erase it. No, I didn't erase it. Cool. So your answer is going to be in 2's complement. If your answer was a negative number, so this would be a 1, and then you'd apply 2's complement to the result. Let me finish up this one, and then I'll run back and do and then I'll run back and do some example where the output is negative on the adder subtractor. All right, so yes, on this one, so if I have my x at this point, I have 4 times x. At this point, I have 2 times x. All right, they're being added together, so 4x plus 2x is going to equal 6x. And then I'm just counting my the width of my buses so that I don't overflow my my result. You said, "Oh, right, thanks." That probably means you got it. Oh, I'm kind of just not flipping it over. I can see where I'm at in the stream, so I'll go back and do an example of the negative, because I think that's important. Even if not for the 3 people who are watching live, and I know one of them's me. Big crowd tonight. I didn't do it on a Friday because I didn't even know we would show up on a Friday. At least I wouldn't. And I'm the one doing it. Okay, so that's basically how you do the multiplication circuit. Division is kind of similar, but I'll cover that after I do the adder where we get a negative number out. Let's say we had, let's just flip it around. Let's say we had 2 minus 5, so A would equal 2, B would equal 5, and S would equal 1. All right, again, we expect the answer to be negative 3, but just to make sure, we'll follow the circuit. A really fun thing, which I've done multiple times this semester, I think, because the 1202 people use Tinkercad now, is actually build this circuit on a breadboard using Tinkercad. And if you think that would make you want to tear your hair out, you haven't experienced it yet because you don't know that it would make you want to tear your hair out. Okay. I think that's close enough to everything being erased. Alright, so input S is 1. My A is 2, so it's 0, 0, 1, 0. My B is 5, so it's 0, 1, 0, 1. this first carry is going to be 1 because that's tied directly to the input as. These XORs are going to act as inverters because I'm XORing with a 1. So all these B terms I need to invert. So that becomes a 1, this becomes a 0, it's a 1, it's a 0. The A term just goes directly into the full adder, so I'm just going to write it closer to the actual full adder. All right, now I can start solving. So 0 plus 1 plus, or 0 plus 0 plus 1 is going to be 1, carry a 0. 1 plus 1 plus 0 is going to be 0, carry a 1. 0 plus 0 plus 1 is going to be a 0, or 1 carry 0. 0 plus 1 plus 0 is going to equal to 1. All right, also carry 0. Again, expecting a negative number, and this carry out here is a 0, so, you know, it would be wrong again if we consider this as our sign bit. But we have 1, 1, 0, 1. So 1, 1, 0, 1. We know this is a negative number because the sign bit is a 1, so we need to invert all the bits. So 0, 0, 1, 0, and then also add 1 to get 0, 0, 1, 1. So because we did 2's complement, we know the original number was negative, and then we know the magnitude of it is 3. I understand now, didn't think of. All right, that's fine, Zygon. I know you probably understood it the first time I explained it, but there were probably, if people are going to end up watching this in the future or rewatching this review for whatever reason, just because it's a party, they probably want to see a negative answer. Yeah, this also gives me a chance to talk about a trick with 2's complement with that sign bit. So if we have 1, 1, 0, 1, right, that's our answer. If we consider this sign bit, so this sign bit is in the 8th place, right? 1, 2, 4, 8. So if we consider the sign bit as a negative 8, and then consider the rest of them as positive, so plus positive 4 plus positive 1, or plus 0 plus 1. So you get negative 8 plus 4 plus 1, this equals negative 3. I didn't learn that in this class, but I learned it later on, and it's kind of a nice trick to figure out with like what that sign bit actually means. It means make that bit negative and then add up the rest of them as if they were positive, and you get the result out. I think I learned that in computer architecture, not gonna lie. But I kind of wish that they explained that more. All right, back to, I think we covered multiplication enough, so we'll do division now. And division, and then last thing I have is minimizing states. And I can also do a timing diagram of the state machine if you really want to. Or, you know, obviously you can ask whatever questions you want to, but we can just leave it open for regular questions at that point. I'll also be doing this again tomorrow night. So if you think of any questions overnight, just drop into the stream tomorrow night and I'll answer them then. But yeah, so division, if I want to divide by 2, this is the same as a right shift by 1. Or probably shouldn't write it like that. I should probably write out the words first. So right shift by 1. So if I have 0, 1, 1, 0, so that's 6. And if I right shift by 1, I'll have 0, 0, 1, 1, which is 3, which equals 6 over 2. Right? Interesting. Again, it's delayed, so I'm glad whatever I said at that point is interesting. Oh, I hate this delay so much. One day these reviews will be in person, but I'm also graduated, so I'll never get to do them. Let's see. If I want to divide by what do I want to divide by next? I don't remember if, or I'm trying to remember what I can get to work nicely. Okay, what if I want to find 0.75 times x? So 0.75, or 3/4. So this is equal to x times 1/4 plus 1/2. This is equal to x right shift by 2 plus x right shifted by 1. All right, so similar circuit where you have x going in, left shift registers, but this is right shift by 2, right shift by 1. We'll add them up. All right, and then there's some things where it's like, if this were a 4-bit number, or let me make this something like 32-bit number, this would be a 30-bit number, this would be a 31-bit number, this would be a 32-bit number. All right, so when you right shift, you obviously lose the 2 most significant bits, or the 1 most significant bit. Oh boy, I go to school in Philadelphia, but this is awesome for my final DC tomorrow. I'm glad, G-Snipe. I'm glad I can help. I also have a YouTube channel. I think Eric shared it before. I didn't see the link, but I do have a YouTube channel covering some stuff. But maybe 8 plus 4 plus 1. Oh, yes, that was what you found interesting. I thought that was interesting too. Thank you, Zygon. Yes. Okay, so if you right shift by 2, you obviously lose the 2 most significant bits. If you right shift 1, you lose the most significant bit. And if you add a 30-bit number with a 31-bit number, you'll get a 32, well, at most a 32-bit number out. So that's basically how you keep from losing any data. And yeah. So next, the dreaded implication tables. And to be honest, I didn't come up with an example for the implication tables. So I'm just gonna grab from slides I did in the past. Ooh, wow, that is a blue glow on my face. Or tabular. Okay. The jog is over here. Okay, cool. So I really hope I didn't have any. Wow, that is confusing. Okay, I'm just gonna go with it. Okay, I'm going to draw real quick, do y'all know how to fill out the application table? Or Jeremy, you're so popular now. Thanks. Thanks, Eric. Do you all know how to fill out a application table? Okay, let me go over how to fill out an application table. And then I'm going to give you another example where there's actually something to minimize out of it. Okay, so I'm going to go back to the example we had in the past. We had state A So this was, I'm just going to do the same 1, 0, 1, 1. I'm going to try to do this as fast as possible. So this was at input 0, so input 1, 0, 1, 1. Alright, so inputting a 1 at B is there. Inputting a 1 at C, or a 0 at C, goes back to A, putting a 0 at D, back to C, and putting a 0 at E, B to C, and 1, get back to B. All right, I think I did that all right. My application table. So first things I'll need is B through E. Do that on this side. I'm going to kind of flip between the two boards because I don't want to do it too small. Otherwise, you're going to miss some stuff. To tell you the truth, granted, I've never had to do a finite state machine at work. If I did, I'm really hoping that there is some sort of software that does this for me. Because there is like circuit optimization software that's out there, which you'll learn about in VLSI if you take it, but I just don't know if it exists for finite state machines only. All right, so we have B, C, D, E. So this goes all the way down. And we have starts at A, so starts at A. A, B, C, D. All right, the first thing we do is we look at what the outputs are. So out is 1, out is 0 for all of those. Remember from the example earlier. Anytime the outputs are different between states, we don't even bother filling those states out, we just cross them. Because they can't be equal. states can't be equal if their outputs are different. And that's the first step. The next thing is, let me see how I did this with B versus D. Okay. So the next thing is on the right, I always put the different transitions that these can go in, or I guess B, C, and D can go in. So on the right, I put the transitions that B, C, and D go in. For example, at B, so if at B, if I input a 0, I go to C. If I input a 1, I stay at B. So over here, since I input a 0, I go to C. So I put a C and a B. All right, so if I input a 0, I go to C. If I input a 1, I go to B. Similarly, on the columns, I always put that on the right. So for all these in the column here, I can put C, B, C, B. Next one I look at is state C. So if I input a 0, I go to A. If I input a 1, I go to D. So since on this row here on the right, I'm going to put A, D. So if I input a 0, I go to A. If I input a 1, I go to D. And then down here, so on this whole column here on the left, I'll put A and D. All right. Next I'll look at is state. I guess I can look at A. I never did that. So A, if I input a 0, I go to A. If I input a 1, I go to B. So this would be A, B, A, B, A, B. And then one left to look at is the D. If I input a 1, I go to E. If I input a 0, I go to C. So I'll put in E, C. C, C, E, C. Okay, now that it's all filled out, start crossing out stuff. We know E isn't equal to anything. Let me make sure there's no questions before I move on. Nope, cool. So we know E isn't equal to anything. So any of these blocks here that have an E in it, we can cross out. So those are gone. Because they all said A was equal to E, and we know that's not true. So we can cross those blocks out. The next one we'll look at is, well, let's just start checking these. Is A equal to C? Well, possible, so we'll keep moving on. We know B is equal to B, so we're good there. So let's check this one. This is A is equal to A. That's obviously true, but is B equal to D? So we check where B and D intersect is here. That's already crossed out. So this is not true. So we'll go back around again. We'll see A is not equal to C because we just crossed out where A and C intersect. So that's gone. A is not equal to C. That's gone. So good job. When we did this earlier, we minimized the states. So the only way that you can say states are equal is if to get to the end of it and there's just no way that you can cross out any more states and there's still states left. But this way we've crossed out all the states. Yeah. So let me pull up an example where I know some will go away. Or where we can say some states are equal. And I'm going to skip to the part where the table's all filled out. Just to save time. Also, I don't even know that I know what this state diagram even looks like. This was kind of just an example I made up. I don't know if you saw that flash, but there's some lightning over there. If you hear thunder, that'll be interesting. I'll be interested to know if you hear thunder on the recording. I'm assuming you'll just ask questions as they come up. But I'll move on until I see any questions. Okay, so this is B through G. So B, C, D, E, F, G. All right, and then it goes A through F. A, B, C, D, E, F. Then the outputs are 1, okay, it looks like the only time the output is a 1 is at D, so cool. Okay, so first thing off the bat is anytime the outputs are different, we can cross them out. So that means the D can't go with anything. Then let me fill out the rest of the truth or the application table. No questions still, okay. B, E, C, C. B, D, C, A. E, D, C, A. Oh, okay. EC, that's right. Okay. So the questions, nice. Now we'll start crossing out. The easy ones is anything that has a D in it, we know it can't be equal to anything else. So these go away. Because we know D can't be equal to anything. All right, so now we'll start going through BE. You need to check where BE intersect. B. Okay, possible. BECC, so still good. Let's see, BB versus CF. So let's see where C and F intersect. C and F. It's already crossed out, so we have to cross this one out. Again, CF is already crossed out. What about AF? AF is also crossed out already. Also has a D in it, so I guess we missed that one earlier. E versus B. Still good. C and F is a no-go. All right, so now we have 3 left. If you look at where B and E intersect, it says E is equal to E, and it says C is equal to C. That is very true. So this is good. So we know that B and E are equal. So B versus E, we said that already. And then C versus C is always equal. So this one's good also. Then we have B versus E, which we said is good, and then C versus C, which is always good. So this is also equal. So what this tells us is that state A is equal to E. So A equals E. A equals B, and B equals E. In other words, A, B, and E are all equal to each other. Oop. I just found out that YouTube doesn't allow others in chat. Yeah. Oh well. Here, I'll figure that out later. So yeah, so this implication table told us that states A, B, and E are all equal to each other. So if you were to rewrite this diagram out, you could just rewrite it using only one of those states instead of all 3 of them. In other words, you just save yourself 2 states. My cat is playing with the wires back here. Okay. Let me see what else was on here. I didn't really have anything else to cover. As far as I know, this was everything. So does anyone have any other questions? I don't know. I'll give it some time. Let's see what I can do about sharing the link. Okay, makes sense. Glad to hear it. Glad to hear it. Oh, why is my cat wet? That's not good. So I'll hang around here for a little bit, see if you guys have any questions, and I'll cover them. No questions from Zygon. That is good to hear. It still just says that there are 3 people watching. Oh, but I have 7 likes. I will like it myself and have 8 likes. Ha! Again, if you guys think of any questions, drop by tomorrow and ask them there. It'll be at the same time, 6 to 8, same channel. I assume the stream I just picked up my cat. Thanks, Eric. Yeah. Yep, no problem, Zygon. Everyone be sure to thank Eric also. He's been doing a great job at this. You know, he took up the role for me last year after I graduated, and he did a great job. He is traveling through the gauntlet that is VLSI right now. And I know exactly how much fun that is, so I'm glad I could help ease the load just a little bit when I can. So y'all be sure to thank Eric for the great job he does all the time. All right. Well, again, you can search my channel. It is type what year is this? So if you search Jeremy Cheney, if you search that, it's going to be a picture. Well, it's going to be the one that says I'm an electrical engineer at Maximum Integrated, because that's what I am. I am a digital design engineer.